Good afternoon, fourth graders. Last week we talked about electricity. We talked about static electricity. Today we're going to move on and talk about current electricity, but before we do that, I just want to do a quick review about static electricity. We talked earlier this school year about matter, and we said that matter is anything that takes up space and can be described. We said that matter is made up of atoms. They're the building blocks of matter. An atom has three main parts. It has electrons, which are negatively charged, which travel in an orbit around the nucleus, which is the center of the atom. In the nucleus, there are positively charged particles called protons and neutrons, which are neutral charged. They don't really have a charge, they're just neutral. It is the attraction between the protons, the positively charged particles, and these electrons, which are negatively charged, that keeps the electrons in orbit around the nucleus. All objects on the Earth have these positive and negative charges. Most atoms and most objects on Earth have an equal number of positive and negative charges. And when there's an equal number of positive and negative charges, we say that it's neutral. We say that that object is neutral. When two atoms or two objects rub together, though, sometimes friction is created. And when friction is created, the negatively charged particles, the electrons, get excited and they can jump from one object to another. And that creates the static charge that you often see when, say, you pull your sweatshirt over your head and you might hear crackle, crackle, crackle. That is actually a flow of electrons traveling from your hair into your sweatshirt. What happens then when these electrons move from one object to the other? Now we say that these articles or these objects are charged. Now we see that the piece of wool that we worked with last week has a negative charge. There's lots of negative charges, more than the positive charges. Over here now we see that the balloon has positive charges. We say it's positively charged. And last week we saw that that negatively charged wool and that positively charged balloon were attracted to each other. We said that opposites attract, negatives and positives will be attracted to each other. And we said that negatives or positively charged articles will be attracted to neutral things as well. But we found that when we had two negatively charged balloons, we found that the two negatives actually repelled each other. That's the nature of static electricity. Lightning is an example of static electricity. Up in the clouds, the water molecules are rubbing against each other. Those electrons are jumping from one molecule to another, creating those charges, and now there's a buildup of electrons that are attracted to the Earth, and those electrons then make a jump from the clouds down to the Earth, and that's what we see as lightning. So that's what lightning is, really an example of static electricity. Well, today we're going to talk about another kind of electricity called current electricity. Last week we said that electricity is a flow of electrons. That makes sense. Currents are really interesting things. Water currents are actually rivers of water that travel through large bodies of water. For example, they can travel through an ocean. We have along the east coast of the United States in the Atlantic Ocean a river of water or a current called the Gulf Stream current. The Gulf Stream current is responsible for carrying tropical storms and hurricanes from the Caribbean, where that water's nice and warm, up along the east coast of the United States. So when there's hurricanes in Georgia, North and South Carolina, Virginia, and up the east coast, that's mostly carried along by the Gulf Stream current. There's also a current in Lake Superior. Have you ever gone to McLean State Park? gone into the water, and when you go into the water you notice that your parents are directly in front of you and you're playing in the water and you might be in there for a pretty long time, and then all of a sudden you notice that your parents aren't straight in front of you anymore. They're down the beach a little ways. Well, it isn't really that you've purposely moved away from them, because you wouldn't want to do that. What's happened is you've been carried along by a current of water, a river of water that actually flows in Lake Superior, not very far off of the shoreline. That's why you have to be really careful when you go boating or you're playing in a raft in Lake Superior, because you could be carried away by that river of water that flows right along the coast on Lake Superior, just off of McLean State Park. Pretty interesting. There are also air currents. There is the jet stream air current, which flows from Canada down across Lake Superior, picks up all that good moisture, and as that current rises over the land of the Keweenaw, what do we get? Lake effect snow. So that river of air that flows from Canada actually brings that cold air from Canada to us, and with it, of course, that great white stuff, snow. So water currents and air currents are rivers of water or air that travel even on this earth through water or through our atmosphere. Today we're going to talk about current electricity, and a current of electricity is just that. It's a river of electrons that flow to create power, to bring power to make something work for us. And today we're going to use current electricity to light a light bulb. So let's take a look at what we have here. Here we have some diagrams of some circuits. A circuit is a complete loop of electricity, and we're going to see if we can light this little light bulb by testing some of these circuits, and you can decide ahead of time, do you think this is going to work? Is this a complete loop of electricity? So here I have my battery, and we said that electrons flow from negatives to positives, right? So here we have the negative side of the battery, and on this kind of battery, the negative side isn't marked, but the positive side is. So if this is positive, this has to be negative, right? So we're going to try this. We're going to take this, and we're going to hold this light bulb on this battery. See, if we were in school, you would have a friend to help you do this. And we're going to touch this wire alongside here, and does that light bulb light up? No. Are we making a complete loop from the negative side of the battery to the positive side? Nope, that's not working. Okay, so let's try this one now. Here we have, see if I can get this hooked up here for us. So we have our light bulb on the negative side. I think I just need 3 hands. Here. Oops. Is that lighting up the light bulb? Nope, that's not working. Okay, let's try the positive side here. So now we're going to touch the wire on the light bulb, and we're going to touch the end of the light bulb onto the tip of the battery, and I am going to touch this wire over to the negative side. Do you think this will light? Well, let's see what happens. Oh my goodness, it worked. Very cool. Why do you think that one's working? Do we have a river of electrons flowing from the negative side of the battery through the light bulb to the positive side? Yep, we do. Okay, let's take a look at the next one. Here we have, let's see how I can do this. Let's see if I can. Oh, I know I can do it this way. Here we go. Do you think this is going to light? Do I have a circuit or a current of electricity from the negative to the positive side? Nope, that's not working. Okay, how about this one? This time I'm going to put the wire underneath the light bulb and we'll see what happens here. Is that working? Nope, that one's not working. And how about this one? Now we're going to just touch the sides of the battery with the wire and put it here. Does that work? Oh, I'm sorry. I meant to have this sitting on top of the top of the battery. Does that work? Nope, it doesn't. Why is it that this is the only diagram that worked? What's happening here? Well, here I can see I have a flow of electrons from the negative side of the battery through the wire to the light bulb and then back into the positive side of the battery. Let's take a look at this diagram here. It'll help us to understand what's really going on here. So here we have our battery, which is our power source, and we have our wire. Our wire is attached at the end of the battery and it flows down into the side of the light bulb. When the electrons flow into the light bulb, they flow up the post inside of the light bulb. You might want to look at a light bulb sometime really carefully, and you'll see that there's a little post in there. Then, between one post and another post is a really, really, really thin wire called a filament. And as the electrons travel across the filament, they actually cause the filament to burn. And when the filament is burning, we see the glowing light. That's the light we see in a light bulb, is actually the filament burning. Then the electrons cross the filament down the other post and then out the bottom of the light bulb, and then back. Where do they want to go? They want to go to the positive side of the battery. Okay? By the way, talking about a light bulb, have you ever taken a light bulb out of a lamp that had burned out? Did you ever shake it gently? Next time you have a light bulb that burns out in a light, just shake it. What do you hear? Do you hear little particles in there just bouncing around when you shake it? Well, that's actually pieces of the filament that have burned up inside of the light bulb. That's pretty cool. So we said that a circuit is a complete electrical loop. If the circuit is closed, the light bulb will light. If the circuit is open, it means that the bulb is off. The bulb isn't glowing. So let's test some different items here to see if they help us to create a complete electrical circuit. So we know that the wire worked. The wire, when we connected or we held the wire to the negative side, and it traveled to the light bulb and then back into the positive side of the battery, that this was a conductor. This copper wire was a conductor of electricity, which means it allowed electricity to flow through it. Okay, let's try the straw. Does this look familiar? It's one from our kitchen at school. And I'm going to attach this straw to the light bulb, just like I did with the wire. And then I'm going to attach the light bulb to the positive end of the battery. Is the light bulb lighting? No. Do you think that this is a good conductor of electricity, this plastic straw? Well, probably not. We call that an insulator. It's something that prevents electricity from flowing. So far, we have the copper wire, which was a conductor, and we have the straw, the plastic straw, which is an insulator. Things didn't flow very well. Electrons didn't flow. Here we have a sort of crunched up piece of aluminum foil. Do you think this will be a conductor or will it be an insulator? Well, let's find out. So I'm going to hold this aluminum foil on the negative side of the battery, and I'm I attached the aluminum foil to the side of the light bulb, and now I'm going to attach the light bulb to the positive side. Do you think the electrons will flow? Let's see. Ah, it did. Cool. So electrons are flowing through that piece of aluminum foil. I bet you never thought about that. But so that's a good conductor. Okay. How about this rubber band? Do you think that this will be a good conductor? Let's test it and see. Okay, so we're going to hold this piece of rubber band, that's not being very helpful, to the negative side of the battery, and we'll attach it to the side of the light bulb, and now we're going to touch the light bulb to the battery. What do you think? Light or not light? It's an open circuit. It's just not flowing. The light bulb is just not on. So, is this rubber band a good conductor of electricity? Nope, it's an insulator. Okay? And we have one more thing here. I have a paper clip that I uncurled. So what we're going to do is we're going to take that. I've attached it now to the negative end of the battery and to the light bulb. And now I'm going to touch the light bulb to the positive side of the battery. Do you think it's going to light? Conductor or insulator? Let's find out. Voila, it lit. So this piece of steel paper clip was a really good conductor. So let's write down what we've learned here. So we know that our conductors were the copper wire and the steel clip, paper clip, and also the aluminum foil. Then we saw that some insulators were the rubber band and the plastic straw. What conclusions then can we make about what makes a good conductor? What do we see? What do all three of these things have in common? Well, they're all metals, aren't they? These are all metals. Can you think of any other things that might be good conductors of electricity? How about water? Is water a good conductor of electricity? Well, why do folks tell you never to be swimming during a thunderstorm? Or why do people tell you to never be under a tree during a thunderstorm? Well, electricity travels really well through water. And you could end up being a conductor of electricity yourself, because after all, what are you mostly made of? You're mostly made of water. So as soon as you hear thunder or you see lightning, should you be hanging around testing out to see if you're a good conductor? Nope. You don't want to be a path to ground for that lightning. So as soon as you see thunder or see lightning or hear thunder, you head indoors. Because a tree, which is mostly water, would be a conductor. You don't want to be standing under a tree. That swimming pool or Lake Superior, whatever lake you're swimming in, or the pool in your backyard, is a conductor of electricity. You don't want to be there when that water is conducting electricity. You don't want to be standing outside during a thunderstorm, because you could be a conductor of electricity. You could get seriously injured or even die when that electricity, that lightning passes through you. Things like rubber and plastic are good insulators. If you notice, on the outside of this wire is actually a plastic coating that prevents electricity from flowing into me when I'm holding this wire. The ends are bare so that they can be connected in your house to switches or in sockets. It's safe to hold on the plastic, but you never ever want to touch the copper ends of the wire because that's where that electricity, those electrons are flowing. So we talked a lot today about current electricity. And remember, a current is a stream of electrons that travel from a power source. The negative electrons flow from the power source into the object that needs the energy to work. Okay, you need to have a complete circuit, a complete loop of energy for it to work. And in order to do that, you have to create a circuit or a path for that electricity to travel on. Conductors like steel or copper or aluminum are good conductors of electricity right along with water. Items like plastic and rubber are insulators which stop or slow the flow of electricity. Before we go today, I want you to think for a second. You know, they call this area that we live in the copper country. Lots of copper was mined here, about 150 to say about 100 years ago. And what is really interesting is that copper from the copper country here was actually used all across the world to bring electricity to many homes. Because I don't know if you realize it, at about the time that electricity was being developed by somebody called Thomas Edison and other famous inventors, people were mining copper here by the ton. And lots of the copper that was mined here in the copper country was used during that period of history called the Industrial Revolution. And it was sent to homes and businesses and factories all over the world to bring light and power to the world. So you have a lot to be proud of as a kid from the copper country, bringing copper, the electrical conductor, to the rest of the world. Have a great day. Talk to you next week. Bye.